There was no audio. Okay, wait, hold up. Hold the phone. Alright, it's working. It's working. Okay. So, yeah, today I'm not gonna do any Erasio programming. Probably. But I will be doing my homework because, yeah, it's getting late and I didn't do my homework yet, so I figured why not just stream my homework. Because I'd rather do my homework than do Erasio programming. Because, yeah, I need to do that. Higher priority. It's higher priority. So, I'm on my laptop right now because I don't know. I'm exploring my options here. Maybe the horrible laptop adds a little bit of flavor to the live stream, you know? The low quality balance with the live stream format. Maybe that will do something. I don't know. I kind of like it. I don't know why, but I kind of like it. So, yeah. So you can see here, I have a chat. Let me test that, by the way. Let me test the chat, see if it's working. Oh, it is working. Can I send a heart emote? Will that actually work? I don't think the heart emote is working. Alright, whatever. We don't need to see all the emotes, okay? We don't need all the emotes. We just need the regular all. Regular all. Okay. So, oh yeah, hold up. So today I got my Hunter x Hunter cup chocolate milk. I put chocolate milk in there. It's pretty good. It's actually not that good, but it's alright. Nah, I'm just kidding, it's really good. It's really freaking good. Alright. So yeah, we're gonna do homework. Yeah, let's see here. Okay. Where did I leave off last time? Okay. So last time I was looking at trees, and this time I'm gonna look at the balanced tree. Oh my god. Is the music too loud, by the way? Test, 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 test. It's that no copyright music, so yeah, it's no copyright music. It's alright. Alright, so we have stuff. What is this? What the heck is AVL? What is that? Okay. Okay, we're gonna write this down. We are going to write this down. So, balanced trees. Okay. So we have an AVL tree. So it balances the height. I see. Okay. So we have AVL tree. Also, let me get the comments bigger here. Can we do that? I don't think so. Can we? No. Whatever. Damn, I wish the text was bigger, dude. Whatever. Okay, so AVO tree. A car. So it's height balanced if for any of the nodes the heights. So for any nodes, the heights of the nodes left and right subtrees differ only by 1. So is this balanced? Oh. Yeah, because this node is the root node and its subtree is 3. And this one's subtree is 2. Huh. How is this not an AVL tree? Says it differs by 1 or 0. 1 minus -1? What do you mean? Oh, because this one has 0. Yeah, okay. Okay, that makes sense. So yeah, this one has 0. And this is 1. And these have 0. This is 2. And this is 1. Okay. Yeah, we're gonna have to make. We're probably gonna have to implement that in a lab, right? Oh my god, no. There's 2 labs for this one. No. Okay, so AVO trees is balancing. So let's say height. Yeah. Also, did I? Okay, I was just making sure. Make sure my screen. If my screen was getting put there. Okay, so height balance, and then a balance factor. Is that so? The balance factor is a thing about the height balance. So balance factor is an AVL tree is when the balance factor is 1, 0, or -1. Left subtree height minus right subtree height. So okay. Okay. So this one is 2 minus 1. Which is 1. What? Why does it say 0? Oh, the height of the subtree. I thought it would be 2. Why does it say 1? Yeah, it doesn't matter. I don't think it matters. So yeah, this is like 1, 2, 3. 1, 2, wait, 1, whatever, and this is 2. Yeah, this one's 2, and this is 0. 2, it's 2. Okay. Let's write that down. So, yeah, we got balance factor. Easy peasy balance factor. Alright, let's go. Oh man, just went back. So let's check this. Is this a balance tree? 1, 2, 0, 0, 1. Yes. This is definitely not a balance tree. This is not a balance tree. Yeah, it's balanced. This is not balanced, right? Because this has 0 and then 2. And then this one, 1, 2 is 0, 0, 1. So yeah, that's balanced, right? What? Oh, it has to be binary. Huh? Okay, so it has to be a binary search tree. Yo, by the way, how do I keep my phone on? Can I do that? I want to keep my phone screen on. I'm gonna need that. Where the heck? Screen timeout. 5 minutes? Never. Oh, what? There's not a never option? That's annoying. Get the hell out of here. Alright, whatever. Whatever. Every 10 minutes it'll turn off. Alright. So binary. So is this a binary tree? So we got 90, 98, 99 doesn't. Yeah, it doesn't. Okay. Oh my god. So an AVO tree is just a binary search tree, except we try to balance it or whatever. The balance factor. Okay. Okay. Is this a binary search? Oh yeah, 64. Okay. I don't know. Isn't it log? thought it was 3. Alright, whatever. What? Oh, it's a worst case. It's no worse than 1.5 times the minimum. Okay. So the minimum is 2. Oh, it is 3, but it's indexed by 0. Okay, that makes sense. That makes sense. Okay. Okay. So we have this is the minimum, and then it's 1.53. Huh. Okay, I have to keep that in mind. So the AVL balances, and it has a better, it achieves a better minimum height than a binary search tree, but you have to rebalance it. Yeah. You know, this is kind of weird. It says if nodes are inserted dynamically, maintaining a minimum height tree requires extensive tree rearrangements, and it's apparently quicker. Oh, yeah, okay. So there's no guaranteed minimum height, but it's like a middle ground. Okay, cool. So an AVL tree is like a is like an optimization, a robust optimization, or something like that. Oh, what? So we store the height or something? Oh. Okay. How do you know what height it's at? Like if you put this here, oh, that's probably easy because like if you insert a node, you can tell the height by the number of nodes you've visited. And I don't know, man. Yeah, so the ancestor node. So the parent node. What do you gotta do with that? You gotta like change its height or something? I'm gonna play that again. Oh, that was... So you just go up the tree recursively? That's no, you can't. It's not recursive. It's not recursive because you only have one parent. So you just go up the tree. What the heck is this doing? So you just go up the tree. That's pretty simple, I guess. Pretty simple. Bro, what? What? Oh. Yeah, there is no relationship. Because this could be at any height, and the balance factor would still be the same. Okay. Okay. You know what? I think I'm gonna put this. I'm gonna put my face here. Yeah. So when adding a new node, what is true about the order in which the ancestor height value is supposed to be updated? Okay. Yeah, that's what I thought. That's what I thought. Okay. This is starting to make sense now. This is starting to make more sense. That's not right, isn't it? Oh my god, whatever. Dude, it is cold in here. It's flipping cold. Gotta put on my goddamn. Gotta put on my shiesty, bro. It's freezing in here. Jesus, man. Alright. Dude, shiesties are so comfortable. Okay, I've never... Excuse me. I've never had a shiesty, actually. I'm just talking about when you put your hoodie like this, you know. It's pretty comfortable. It's pretty comfortable. Okay, so what? Okay. Let me mark this down. Okay. Bro, what's today? Today's Friday. God damn. God damn. Oh yeah. Look at this, bro. Boom. Hunter cup. I love this cup. All right. Okay. Back to business. Back to business. Okay. Okay. what is this? So rotation. So what is that rotation? I'll call that rotation. Yo, by the way, I gotta. Okay. So rotation. What is this? So how do you rotate? I mean, this makes sense. Dude, it's still cold. My forehead is cold. My forehead is cold. Okay. So this makes sense, right? Because we got 3 nodes, and one of them could be in the middle here, like the root, but they're all like separately. They're like in a line. So we would like to pull this thing a little bit. So let's see how that works. Yeah, it violates the height thing, right? Oh, that was pretty easy. Huh? Can we do that? Can we just do that? That's pretty easy. We do a few things. So this node goes here, this node goes here, and this node goes here. Is it as simple as that? So the rotation is at node 86. So 86 is like in the middle, and then it becomes its own right child, and then these move up. So 75 turns into the parent node, and 30 turns into the left child. Interesting, very interesting. So 89 goes to 3, 17 goes to here. Oh, here's another one. How do you do this? Huh. Ooh. So what happened? So A, B, D. Where does C go? Huh? That's weird, isn't it? So B's former child. Oh, I think that's it. No. Oh, is it? I think we good, homies. I think we good. I just have to check, bro. The jump scare. I gotta check the jump scare. Alright, hold up. I think we good, bruh. I think we good. What? Oh my god. Oh my god, I think we good, bruh. Alright, whatever. Let me go back to the chat. Oh, fuck. So it says B's former right child C becomes D's left child. Is that what happens? Can this get really complicated? It could. Or not, you know. Okay, so this case... Does it just end up like this all the time? Like the left one? If the left one looks like this, then the right one would always look like this? Okay, so, because I get this, right? A, B, D should go there. That's what they said to do in this one. But what about the C right here? God damn. Oh. God damn. What does C do? I don't know. I do not know. Jesus, no. Stop. I actually gotta check. I actually gotta check that. I gotta check it. Okay. Bro. What the heck? This seems kind of weird. I mean, this makes sense, right? It would go here just because they said so. Alright, whatever. I'll allow it. So we have 53 is N3. 27 is N1. 9 is N2, and then, yeah, I guess. Oh. Uh-oh. What the heck is this? No way, bro. Rotate left? Hell no. Hell no. So 51 goes to N2, right? 60 goes to N1. N6, 73 goes to N3. N6, 73 goes to 60. N3 is 73. And then N6 is 82. So we just N4. So we just have these two. So 25 is N4. Bro, what? So 57 is. I think I get it. I think I get it. So if we're doing a left rotate, all the left children on the right side have to go on, they have to be in the same height and then become right children up the left side. And if you do a right rotate, I guess it's the opposite. Vice versa. Oh no. What is this? What is this? Hold up. Let me check if this is too hot. I think we're good. I think we're good. Alright, there we go. Dude, this camera. What the heck was that? I think there's a gust of wind in here or something. It's just so weird. Wait, it didn't work. What if I go like this so you can't see me do it? It wasn't me. It wasn't me. Okay, so we have an algorithm here. It updates the height by taking the maximum of the child subtree heights and adding one. Why do we add one though? Okay, well that's cool. So do we call this, when do we call, whatever, and then, so that's the update height. We have set child. Sets a node as the parent, so left or child, left or right, excuse me, left or right child. Okay. 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 So we got tree rotation and these things. Oh my god, I gotta zoom in. My poor old man eyes. Okay. Wait, hold up. Set child. Update height. It updates the parent height after setting the child pointer. The child must have a correct height value. Bro, come on. Set child, bro. Get the freak out of here, set child. Alright. here's the rotate. Here's the rotate. That's the algorithm? I thought it would be more complicated. Replace. Huh. I thought that would be more complicated. You also, my pants. I gotta put them down because it's cold in here, bro. My freaking legs. Alright. My feetsies. My feet's gotta get comfortable, bruh. My feet's gotta get comfortable, bruh. Alright. Alright, that's much better. Oh my god, dude. Let's see here. Hold the phone. Hold the phone. So this rotates right. So the left. Wait. Load. Node left. Right. So if the node parent is not null. So if it has a parent. We do tree replace the parent. Huh? Why is there 3 of these? What does this do again? Replace parent, current child, new child. Okay. We need to supply the current child. Makes sense. Alright, whatever, bro. So replace. Wait, that's the parent, right? Okay. So what the heck? So we do AVA tree set child, the left child of the node with the left right child, and then we also do the left set the right of the left. Jesus, what does that even mean? Let me just imagine what this would do. So D B T1 C would be the left child of here. Oh, that actually makes sense. Okay. It actually makes sense. I don't know why. I still don't know what this is doing, though. This is kind of crazy. Oh my god, there's only one step. Oh my god, this better be right. So we got the node. Alright, it's just like magic, I guess. Node B's right child is null. Maybe? I mean, it says set child. That's that one. So set child. Yeah, it still works, right? Again, these left child is null. No, it won't work. Yeah. Hold on, what does this do? No D. Maybe a subtree of larger tree? It is. It's part of P. So, yeah. It says the algorithm updates node D's parent to point to node, yeah. Yep, updates. Oh my god, what is this? So we rotate... Okay, so... we rebalance a node. And then I think tree is the parent? The freaking... the root node? Rotate left. Tree. What does tree do, by the way? They supplied tree here, but they never used it. Oh, never mind. Tree root. Okay. My bad. They do actually use it. They do actually use it. So... okay. So what are they doing? They do rotate. Dangy. Double rotation. Alright. I'm gonna write that down. Rebalance. Alright. Bruh, what? Rebalance. I thought it did this. Recomputes the height values. Alright, I guess. Ooh. Okay, so update heights. Requires the stuff. The heights to be accurate. Oh, it does. Okay. God damn it. You know, I didn't even check the algorithm. I should have checked it. But it, you know, it calls rotate, which might modify the height because it calls these methods replace and set child. So that these two. Huh. I don't. Oh yeah. Okay. Here it does update it. Set child updates it. Yeah, so it does, Yep. That's the first operation. What? Oh. Yeah, my bad. My actual bad, bro. Oh my god, what is this? The balance factor thing. What is it? So we got 0, 1, 0, 1, 2. Okay, so 20 is 0. 68 is 0, 1, -1. What's 1 minus -1? 2. Uh-oh, we have to rotate. I think we rotate right on 68. Please. It is correct. Oh my god. Okay. Okay. Alright, so when we insert a node, we might have to do a rotation. This is 0, 1, 2 thingy. Oh my god. Oh my god. Double rotation is needed. You know, they did say that on the rotate algorithm. They said that. They definitely said that, right? Where is it? This one. Oh, yeah. Yeah, they call it twice. They call it twice. Here they do if. Oh, so they do 2 checks. Okay. So this one needs a right rotation on C. But it turns out weird, right? What the hell? Oh, rotate left at A. And then rotate right on C. But how are we supposed to figure that out? Left and right indicate each. Oh, lordy, lordy, lordy. Oh, yeah, my bad. After the left rotation, where is the right rotation performed at X, Y, or Z? At Z, of course. Where is Z after that? And 3. Yeah, after the left rotation, and then the right, where is Y? Left. And 2. What? Oh, Y goes here. Right? Okay, N1. Whatever, I just... Okay. Where's X? Ding, and 2. Oh, where would Y be moved if we did only the right? And 6. I think. Yeah. Oh my god, what? The heck is this? What the heck is this? What the shklibbity? So we have, if we insert a node, oh my god. Okay, so we have left On this side, go left, right, and then right, right, and then, oh my god, right, left. Bro, what is this? What is this, bro? What is this? Okay, so Z's balance factor is 0, 1 minus, so it's 2. And then W is 0 minus negative 1. Okay. I don't want to. Alright, what is the proper rotation for A? Right at Z. What is your proper rotation for a 2, negative 1 case? Let's take a look. So we're supposed to do 2 things, apparently. What the heck is this? So left, so we insert here, and then the heights. Oh, I see. So we get the heights of the parents, 2 parents above it, or something. That's awesome. Alright, so insert, have a bunch of cases. You know, I should write that down. I should write that down. So we have a veil insert. Yeah, there's 4 imbalanced cases. And then it tells us the rotations that we need. So okay. So if it's parent, so it's like 1, 2, then we gotta move right. What the heck are these numbers, by the way? 0, 1, 2. 0, 1. Oh. So the height of this node is, max height is 2. Max height of this one is 1. So like parent, parent. Then we do a right rotate at the grandparent node. Right? Right rotate at the grandparent node. Okay, so it's going down. Well, it's always going to go down. Okay, if they're the same sign, then we do 1. Oh, okay. So, why is this negative? Oh, it tells us which side we're going to do. Yeah, okay. So if the left side... Oh my god. Okay, so if the left side is longer, then we have to do a right rotate. Left side meaning it's going to be positive. If the right side is longer, meaning we're going to have to do left rotate. They're both going to be negative. Okay. So what do we do here? We do... So if it's negative, we gotta do a left rotate at the first parent on this one, the first parent, and then on the grandparent, we gotta do a right rotate, I guess, because it's positive. Okay. Okay, let's figure that out. So, two negative ones. So we're gonna do a left and then right. Wow, that's Jesus Christ. Okay, what about, so what is this? A phone book? Oh, so it's to keep the searches quick. Searching with rebalancing. So what do? We update the balance factors and then do rebalancing. Okay, that's pretty simple. Pretty simple. Dude, I'm like a little tired, but I don't know why I keep yawning, bro. I'm not doing it on purpose. That John is on automatic. Alright, bro. I'm trying to mix the milk. Because, yeah, bro. Chocolate is not mixed. Trying to mix it up. Okay. And let me check is it looking good, I think? So is that, can we see the text? Yeah, we good. Okay. So if we have insert, we don't have to rebalance. Here we insert again, but this time we do a left rotate at atom because negative and left, so that's cool. We add and that's good. Okay, here we do a right rotate at Eddie and then a left rotate at Chan. Yeah. Okay, so parent, oh, what? Huh? What the heck? Car? Why is car? You know what I don't understand? Why? Oh, we go to the first two. And okay, it's not necessarily a parent. Alright, that makes sense. Okay, so here we have these. So we do a right rotate at Dan and then a left at Bu. Okay, makes sense. So if it has X levels, the first X minus levels. What? Alright, fine. Yeah, it is logarithmic though. It is logarithmic. Search. It's, frick that. What? Oh, they're all logged in. Oh, this is constant. Okay. Okay. Hmm. Hmm. So this is the search. And then this is the rebalance. Alright. Yep. Oh my god, dude. What? Oh. Yeah. What? So it adds it, but the new node's parent is not set. Oh, I don't get it. I don't know about that. Okay, that's pretty cool. That is pretty cool. So that's insert. Here's remove. So this is very similar to insert. Ooh. So remove 63, and then we have to rebalance here. Remove 84. let's see what happens. Okay. Okay, and then it has to rebalance. Yep. Okay, and then we remove 84. Oh, okay, we just replace it with that. Excuse me, 0, 1. Okay. Wait. Okay, if we remove 93, this is -1, and this is 0, 1. So this is 2. And this is... Oh, what? It's as simple as that? Okay, I guess. Okay. Alright, let's look at their, let's put AVL. AVL remove. So it's pretty much like the insert, except we're removing a node instead of adding one. So that makes sense. Wait, what? Parent up to the root. Oh. What? After removing node from AVL tree using the standard remove algorithm, all nodes. Nope. Yeah. Alright, I got that. I don't know. Oh my god, dude, no. Oh, okay. Oh, that's why they got the balance. Okay. Oh no, BRB. Alright, I'm back. God damn. Oh my god. Alright. This is the remove, right? Yeah. So if it has 2 children. Oh, okay. So we copy it and then we remove like the successor node. What the heck? Okay. So 70. Bro, what? The freak? Oh, we need to find a replacement. Is that how that works? Yeah. So we go to the right tree, and then we look for a replacement node. Okay. Alright, so we do that. And then we copy the key from the successor. So, and then after we do that, we recursively remove the successor. We do it all over again. Right? So, if 73 has... excuse me. What is the case for that one? Replace node with node right. I think it sets 73 to null. What? Bro. Are you kidding me, bro? Oh, this. What? You kidding? What? Oh my god, what? Yeah, because it does this. Does it? No, it calls it. Oh my god, it calls. Yeah, and I just freaking replace it with its right, which is null. Oh. Wait, I'm actually confused now. If null is null, return. No, I'm confused. Oh, I gotta check all the goddamn checks. What? Is this even correct? I mean, it checks this one too, you know. Why isn't this an answer? It checks this one. Node equals tree root. That's not even a freaking... I'm not doing this. I give up on this. Alright, let's G. Let's read this. Traverses the tree from the root, and then it goes up to rebalance. So at most, 2 rotations are needed for a single node. 1 node is visited per level. And there's around log n levels. So yeah. Makes sense. Makes sense. Makes sense. So nodes are a little more complicated now. A little more complicated. Oh my goodness. Alright, let's just skip. Dude, what the heck, bro? Now we're doing red black tree, bro. Alright. I don't know what red black tree is, but we're about to. We're about to find out. We're finally on AVL trees. Nice. So this is self-adjusting heuristic tree balancing. Tree balancing. Yeah. Yeah. I'm just looking around at my notes. Dude. Okay. So we have hash tables, which I don't think I needed anything else from this. Hash table, and then there's a binary search tree. trees. And then there's the tree. That was cool. Okay. Okay. So also the linked list, which is pretty easy. Okay. Binary search, sorting, divide, conquer. Cool. So we went through a few of these. So I did a list. Dynamic array, I think. Stack queue, DQ. Set I did not do, but that could be a hash table, I think. And then priority queue. What is that? Priority queue. I don't know if I did that. Did I do that? Dictionary map. I didn't do that one yet, right? That could be a hash table, right? A dictionary or a map. Isn't that a thing? Hash tables. Alright, makes sense. Makes sense. Okay, so now we're at balanced trees. We're at balanced trees now, okay. Guys, BRB, bro. I gotta go to the freaking bathroom again. Okay, I'm back. Also, let me rename that. So, screen. I'll call this live screen. Okay. So. Okay, so. Red. Black tree. Dude, this always like on mixes every time I do this. So this is pretty similar. Oh my god. So is red black tree better than AVO tree? Cause the AVO tree also ensures that it has a height of this much as well. But whatever. So each node is red or black. The root node is black. Red node children cannot be red. A null child is considered to be black. All paths from a node to any. What the freak? That's a weird condition. All paths from a node to any null leaf descendant node must have the same number of black nodes. So this one to here, the path is not good because this has 1. Oh, it has 2 nodes, and then this has 3. So that is okay. Let's take a look. Okay, I don't think they're gonna show us how to balance it right now. Yeah, because they have rotations. Yeah. Bro, hell no, bro. Alright, I don't care. Yep. Huh? Oh. Oh my Jesus. So 75, 50. No, it's 2 black null nodes. 75, 50, 20 null has 3. Okay. I think this is a okay. Oh, come on, I didn't even check. Yeah, the right one is larger, so 71 black. That makes it look symmetrical. So black nose children will always be the same. Nope. All valid red-black trees have more. Nope. I mean. Okay. Oh, screw this freaking ordering, bro. Screw the ordering. I don't care about the BST ordering. Alright, yeah. Alright, I'm gonna do this. Oh, I could have just. But actually, yeah, let me do that. Okay. So we got rotations. Yeah, so we got rotations. I would assume. Oh, it's like the same. Okay, 17 goes to N2. 32 goes to N1. And yeah, oh. Altering up to 3 child subtree pointers. Okay. You know, let me check the live stream real quick, see if it looks chill as hell. So chill. Alright. looking good. Looking good. Arbitrary that child. Damn, that balances it. That actually balances it. Because if you make this right... Wait, how does it go? So this one goes here. This one goes here, and this one goes here. Okay. How does the coloring work? Do we just... How does the coloring work? Alright, let's check which ones are valid. So we have... This satisfies the BS2 ordering. The root node is black, and we have... This is not a valid. Yeah, this one is not valid. This one's valid. It's only true. Wait. Let's hope they don't do some. Okay. What? Oh yeah, no, yeah. I got the right answer. Oh, so they're related. They're related. Oh, right at 66. 3 yields 2. What? Left on 41. No. A rotation at node. Right, it's probably false, right? Alright, let's write that down. So we got rotations. Rotation. Okay. So inserts a node such that all the requirements are true. So inserts begins by calling insert your generic binary search tree insert, and then it is colored red, and then a balance operation is performed. What? Alright, I mean, do we ever... What the hell? So this is the balance. Jesus, bro. Do we... Oh, yeah, we do stuff. This is a little different. This is a little different than the other one. So the balance on the AVO tree just kept track of the height and rotations. The red-black tree balance has us rotating and changing the color of nodes, which is a little, I don't know, it's a little different. A little different. The heck? What the heck, dude? Oh my god. So there's a different... Oh my Jesus, dude. Okay. Oh my Jesus. After this, I'm playing freaking Horacio, bro. This ain't it, brother. Oh, this ain't it, bro. Nah, this is it. What am I saying? This is actually totally it. This is homework, bro. What? That's crazy. That is crazy. I said the stream would be not crazy. I didn't actually say it. It's in the title. Not crazy homework stream. Yeah. 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 Alright. Do I really want this to know about this? It's what the freak is this, bro? So we got balance, tree insert. Okay, let's read this. I was gonna say let's figure this out, but not much to figure out. Not much to figure out, is there? Dude. So we insert 22, and then it'll check if there's rotations needed or tree balancing. Oh, what the? Okay. So if the parent is black, wait, what? Let's see. Whoa, hold up. So we called what? Oh, so it did something. It did something. So it does parent, grandparent, and uncle, and then okay, we switch some colors and then we rebalance at the grandparent, I think. Alright, that's interesting. And then we put 44. Parent not null, parent is not black, parent, grandparent, uncle is null. And there's a case for that, apparently. And then what the, okay. Oh my god. Oh my god. Okay. Okay. What was that? That was the, wait, I just skipped that. That was the insert. I didn't even write that down in my notes. Alright, we got insert. Okay. Okay. So we got remove. which is the first node it finds. What the heck? Okay, we gotta call prepare for removal. We do a different thing. So this is similar to the AVL tree remove. Okay, and then we do this. What? And then we remove it after doing all that? Thought we already removed it. Oh, no, we just replaced. Okay. Yeah, that makes sense. That makes sense. So here we do replacing some stuff. Here we balance it. And then we remove it after all the stuff. So what does this do? Oh. Okay, it restructures it. So if it's a black node, it does this. What? What? That is interesting. Bro, I don't know. The node's predecessor? Sure, I guess. Oh my goodness. What is this? What the heck is this? Are both children black? Well, what? Return true. Oh. Okay. Non-null and red. Get sibling is called on a node with a null. Parent. Node parent does not equal null. It just does null. It just returns null. Is null or black? Is null or black? Nope. The node parameter must be non-null. What? It probably gets sibling. Yeah. Oh. This one? Oh, yeah. I don't even care, dude. What the heck is this? What the heck are these? There's more what? Case 2, 5, or 6? Why are there so many cases? My poor phone is running out of battery. Can I charge my phone from my laptop? I don't know. Do I have an extra plug over here? Do I have an extra plug over here? I don't know. I don't think so. Alright, let me go find that. Let me charge my phone real quick. Let the rope go. Alright. I found a Minecraft charger. This is the one I use. This is my main charger. My main charger. Minecraft movie. Isn't that interesting? Alright, I'm back. We're so back. Alright, let's do a lock-in moment with the camera. Hold up. There. I'm trying to align this so I'm like right in the middle of the camera. You don't know how to. Oh, there we go. I figured it out. I have to aim at the camera with my hands. Alright, there we go. That was the, I don't know. That's how you code, man. You gotta do it before you code. Like, I don't know, at least once. Or else. Oh, look at this. Boys and girls, here is USB A to USB-C. USB-A female to USB-C male. You know why they call it male and female? Because the female is where the insertion happens, and the male is where, I don't know. That's sort of weird, I guess. Yeah. The male end is like the, it's usually smaller. Yeah, it fits into a hole. And the female part just is like a shell with a cavity in it. And then it fits like a piece, the male counterpart. And it has a bunch of connections here, bro. USB. USB kind of cray. It's kind of cray, bro. There's like a protocol. USB-C has so many wires attached to it. I'm curious. Alright, we're going off schedule. Let's search up this. Look at this, bro. Look at that, bro. What the heck, bro? What the flip? There's so many pins. Yeah. and they are mirrored. You can see here they are mirrored. Ground. Here's TX1. Oh wait, they're not mirrored. Oh, I thought they were. Huh. That's pretty cool, right? Because you have two. What is this? TXD plus. Oh, these are for Super Speed Plus. Whatever that means. And here's secondary bus. I don't know what that is. Alright, whatever. So we got that. We got voltage. I think. Ground. Data. So the transmit, receive. This is your generic. Oh, this isn't generic. This is 2.0 high speed. Yeah, this one USB 2.0. So that's pretty cool, right? There's a ton of pins on here. That's crazy. It's like symmetrical or whatever. Alright, that's cool. Yeah, USB's crazy. Oh, wasn't even sharing my screen, bruh. Bro, I was just looking at this. Yeah, I was just... Yeah. Anyways, what freaking time is it, dude? It's like 11. Oh, dude, because I went to sleep late yesterday, so... Wait, did I? No, I didn't go to sleep late. I actually just woke up. I just slept too much today. I just slept too much, but that's alright. That's quite alright. Okay, so I was looking at this. Prepare for removal. So we do this. What? Okay, then we gotta do sibling. Yeah, that's just a bunch of stuff. Oh my god. You know what? I want to know the time complexity. What's the freaking complexity of this, dude? What is the complexity? B-tree. Ooh, that's cool. That's actually cool. So it's like a balanced tree, but it's not binary. Oh. Cool. I mean, that's pretty cool. B-tree. I should probably learn that, huh? Let's search up AVL tree. What's the complexity? Oh. It's actually the same, is it? What? What? When would you use AVL tree versus Oh. Cool. Okay. So AVL trees are better for lookups. Red-black trees are better for insertions. What? So red-black trees take up less space in memory, I'm assuming. Let me close these freaking email. What is that, new tab? Get that out of here. Okay. Tree map. Let's take that out. So Java says they do login time cost for that. Where the heck is, where does it say it's a red-black tree? Red. No, bruh. Black. Whatever. What flipping ever. Okay. So that's a little bit of history there. That's good. So red-black trees are actually more popular, maybe. And it's used in Linux, I think, in the kernel. So I might have to, might want to know this. Might want to know this. I feel like AVL trees are simpler. And like in their implementation, it's simpler. Because here there's like 6 cases apparently. Yeah, there's like 6 cases here, bro. Alright, let's figure this out. So what does this do? Oh, okay, I see. So it's like a little finite state machine, kind of. So if the node is red or the node's parent is null, we do nothing and we stop. We halt. Okay. So there's 3 halting cases. So we have the parent is black, and both of the siblings' children are black. And we have parent is red, and both of the siblings' children are black. So if either one of these happens, then it would halt. Okay, and if this happens, the node is red, we halt. Or if the node's parent is null. Okay, so if a sibling node is red, we color the parent red and the sibling black. So we switch their colors. If the node is the left child, what? If node is left child of parent, rotate us. So we rotate if we have a red sibling, but we don't halt. Okay, and then here we do sibling's left child is red. I see. So these two are pretty much mirror conditions, and these as well are like mirror conditions, kind of. Yeah, and then these two are just whatever. So this is like parent is black, both siblings are black, both siblings' children are black. Here we're the same thing except the parent is red. It does a little more when the parent is black. So color sibling red and call remove oppression on the parent. And if the parent is red, we color them black and the siblings red. And then we halt. Okay. So if the siblings love child is red and the thingy, and notice a love child of the parent. Siblings love child or siblings right child? Okay. And then node. And node is right child of parent. Okay, then we color sibling red and the right child black, and then rotate left at sibling. God damn it, bro. What are these freaking cases? What are these cases? Dude. Oh, I'm crashing out, bro. I'm actually crashing out. I don't want to know this. I really don't want to know this. But I might have to know this. Okay, I'll see what I have to study. I'm not gonna totally study it. The balancing of a red-black tree. But if I see it on the exam, on the practice exam, then I will study it. So that's removal. That was for removal. That's crazy. That is crazy. Okay, so we have left and right, as well as parent and color. Yeah, so we have stuff. I don't want to know about this. I want to know about... Oh my god, dude. Yeah, this is what I want. So we have insert... Insertion balance? What the freak does that do? Oh, we gotta do insert balance. Okay, what about remove? Yeah. It says a search method. Yeah. Search, remove node. Fair for removal. Okay. Okay. Prepare for removal. What is that about? What? Do we use that? Remove node. The heck? Replace child. Does replace child call the what? Oh, okay. If the node is black, prepare for removal. This is a weird data structure. Yeah, this is kind of weird, but okay. All right, that's that. All right, let's do the freaking lab. All right, let's do the lab. So let me get my wrist support. Wrist support is good. Yep. And there's some code here. Let's expand this. Oh my god, what is this? What do we gotta do? So we have a node and get nth key. Okay. All right. Let's inspect it, bro. Well, we do have a few things at our disposal, right? So the only thing we don't have is that one function. What? Or where's that one function? Huh? Oh, binary search tree. That right there. So this is even larger. This is even larger. Oh my god. So I have to implement this. Is that what that's saying? So we have an in order traversal. Yeah. Insert, remove key, search, insert node. Make a new node. Yeah. Remove node. Oh wait, hold up. Hold up, what does it do? Okay, that's that. Ooh, we have our even... Uh-oh, we have rotations. That's not good. We need to balance something, right? Alright, whatever. Alright, that's cool. That's cool. So we got that. And it says AVL node extends BST node, and then we have AVL tree extended. What? AVL node has this. Ooh, it even has get balance. Stuff like that. Cool. Extended AVL node. So we're gonna have to add stuff to this. Subtree count. Ugh. Oh my god. Alright, there's another thing. Where is it? AVO tree. And it even does rebalancing. Okay, that's cool. Cool. So it does all of that. Your typical stuff. We have extended AVL tree. Ah, so that's what we're doing. Right? That is what we're doing. Yeah, what is this, by the way? So inherits thingy. Yeah. Number of keys in the subtree. 2, 3, 4. What? 1, 2, 3, 4, 5, 6, 7? So isn't this number just how many nodes are under that node? Oh, oops. How many nodes are under that one, including the node itself? So this has 1, 2. This has 1, 2, 3, 4. 1, 2. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. Oh, I get it. So we're gonna need to do some balancing. Some type of balancing of this subtree thing. Is that what I have to do? Let's figure this out. I'm probably gonna have to, I don't know. Okay, let's see. So we gotta implement this and this. Complete the implementation. Do not implement this. Oh, this is what I gotta do. Okay. So I have to override some methods to make sure that the subtree key count is accurate after an insertion or removal in AVL tree. Okay. Okay. Yep, look at that. MS Paint, the greatest painting program there is. Okay. So here's what I'm thinking. When you insert, let's say we have this, right? This is our tree. Let's say it's like 5, 4, and like 10 or whatever. Doesn't really matter. It actually doesn't even matter. The only thing that matters is the count. So, yeah. The subtree count. So, so let's say we add a node and it goes here, denoted with dotted line. So we do that. What's gonna happen is stuff is gonna happen. Stuff is gonna happen. You know what I could do? I could do like a like an update algorithm, like an update thing. So So here's what I'll do. So I will call update on this node parent, and what it's gonna do is increment its count by 1, and then it's gonna go up the parents and do the same thing until it hits the root node, and it's gonna stop. I think that's it. I think that's it. That should be the algorithm. That should be the algorithm, right? Because if I add a node here, you know, this should increase by 1, and then its parent should increase by 1, and then its parent should increase by 1 until you hit the root node, which is this one. So that's when you stop, because this doesn't have a parent. Show. I think that's it. So I'm pretty sure that's it. Alright, let's look at the AVL node. Yeah. Let's look at that. Is this read only? Can I? God, why? Why you do this? Why you do this? Let's do extended AVL. So extended AVL, yeah, I wish this had a parent variable. Does this have a bit? Oh, thank God it does. Yes, sir. All right. So, yep, that's it. That's it. Yeah. I'm gonna put the update subtree count. Alright. So you're only supposed to call this on the parent node. So I'm just gonna do this. So the node itself is, wait, hold up, because the tree, okay, so here we're gonna do this, which is the update subtree count. Yeah, does the stream look good? Okay. So I completely forgot what I was doing. All right, I don't know. If self, wait, hold up. You can't call this, right? Is this isn't callable, like, from, this is supposed to be static. So yeah, if node equals none, nope, I'll say node.parent equals none, stop. Yeah, we return again. Else we do this, which is that simple. We call it on the parent, and when we're here, we do this. Yeah, we just keep going up. If we have a node, the increment, and if the parent is none, that means we don't do this anymore. Oops. I could simplify this a little. I don't want to. So I think that's I think that's it for that. And then on the node, they said I had to override something. What do we do? Get height. Okay, what do we do? Superset left. Can I just override methods from here? What? Oh my god. Okay, this only works. This little thing works only on a leaf node. Because we go upwards from the leaf node. But if we don't add a leaf node, then it's not gonna work. Oh my god, I've heard this song before. Borderline genius. Damn. God damn, bro. Borderline genius song right here. Wait, hold up. This might not even be no copyright. No, but let's go back to no copyright. Damn, bro, if it's Borderline Genius, then, you know, it might get me copyright striked. Dude, that's what I get for not putting it. Alright, whatever. So... So this works on the root, the leaf nodes. Right. I think this is supposed to happen when we insert I think insert, let's see. You know, let's call, no, this is, let's do something here. Let's call this propagate, insert, and let's make another one called, like, remove. Yeah, if we remove one, it's gonna, so these have to be from leaf nodes, like, apparently, and so you can't remove with this, right? Alright, let's look at tree. So an AVO tree. Oh my god, dude, we gotta do like a rebalance. So that's something I don't know how to handle. let's look again. So we have insert, right? We do that and then we do rebalance. Okay. I think we have to handle the rebalance thingy. Probably. So every time it rebalances, I think I have to do something. I don't know what to do, but you know what? This is nonsense. Alright, this is nonsense. You know what I'm gonna do? I'm gonna do a different not that one. I'm gonna do a different algorithm. I'm not doing this. No, I'm not doing this. I'm gonna make it go downwards. So propagate down. Update. So it's gonna go down. From a node and update all this stuff. Yeah. So we're gonna go down. Yeah. So how do we handle that? How do we handle that? That's kind of weird, isn't it? Because we gotta go downwards? Okay, what if we did a thing where we went down and then we go back up or something? Like if we went down to try to find all the leaf nodes, you know, we do that. Okay, what if we do like a little dictionary? This is crazy, guys. Come on. What the heck? What am I supposed? Because like if you go down the tree, look at this. Because if you go down the tree, right? All right. If you go down the tree, because like if we insert here, we might have to do a rotate here, which means I would call what's it called? I would call the update. Basically, I would just call the update on the root, which is not actually ideal. It's not ideal, but it still works though. It still works. So, yep. So what we do is we split between the children. What do we do? Get height. We can do that, right? Get height. Isn't that a thing? It's not a thing? Maybe in this one? Remove key. Remove node. What? There's no height thing? Insert. Dude, what? I swore I saw a get height thing. Huh. I guess I'm gonna do that myself. Alright, let's do that. So let's look in here and let's do a get height So we're gonna do... No, it's not the gate height. We're just counting how many nodes are there. Okay, that's not right. That's not right. So I'm gonna call this get subtree count. Bro, it's just screw this. I'm gonna make an algorithm. So what I'm gonna do is make a recursive downward search or something. Is that what I'd be doing? Because like you would start here and then you'd be like, okay. Wait, so it would stop here. And then how does it know to return, like return upwards? We gotta like fork, dude, it's weird. So we gotta do like a new recursive call for this. Okay. We're just counting. So you do the nodes of this. Alright, hold up. Let me just let's just do this current count. Current count equals 1. So we're gonna do so okay, I'm gonna do if self dot left equals none. I'll say left none, and then right none. So if left none, if left not none, what the heck am I doing? What the heck? What? So if both the children are none, we're in a leaf node. And then we just return current count, I think. So left none and right none. Okay. So if we're on a leaf node, we return 1. Okay. So if it has 2 children, we're gonna return current count plus that and that, so yeah. Oh wait, my bad. If left exists, then we... Okay, so if left exists, okay, and if right exists, and if they both exist, then we do this one. So that's the old algorithm for that. That does that. I hope that works. I mean, I don't know if it works. I really don't know. I really don't know. Bro, what? I'm gonna do this. Just to help that out. Should I do that? I don't know. You know what? These I could actually just move this like that. Yeah, let's just do that. Okay, so that's that. What am I supposed to do? So yeah, so let's do this. So let's override methods like in here. I mean, I already overrode that. Set left. So this doesn't do any like rotations, right? I don't know. Alright, whatever. Let's just run the program. Runtime error. Can you tell me what the error is? By any chance? That would be good to know what error it was. What the heck? Bro. Standard out, bro. Give me the error. Give me the error, bro. Can I edit this? Oh my god. Oh my god. Why you do this? Why you do this? Oh, I didn't implement this. But what? It says pass. What the heck? Why does it say runtime error? Bro, like, give me the error. Tell me what the error is. Is the tree? Because it does this? Or what? So get nth key. What does nth key do? What? I mean, I get the subtree count, but what's nth key? What? Oh. Oh. Okay, it says don't implement get nth key. Okay, what are we doing again? The heck? So the tree and this. Okay. I mean, it says this is weird, right? Hold up. This is weird. You know what? Did we get I don't know why it didn't work. Whoops. Okay, whatever. So test one. Let's look at test one. Let's see. So we got test one. Yep. So we did tests insert, verify keys, and subtree counts. So insert verify keys. Okay, so do we insert keys? Hello? Like... This is test one. So the subtree breaks, right? Because let's look at the tree commands. Look at tree commands. Okay, yeah, that's that. And in order key verification, right? And then the last one fails, right? So what does it do? What does it do? You know what? We should probably check if it's null. Don't you think? Because they might throw us a stupid, like... That actually makes no sense, though. Because if it's null, then how would you even, like... Reference? Then it's not a valid tree. What? A circular reference. Circular reference. That's great. That is so great. Okay, so it says... Okay, it does this, not this, compare actual. So I'm pretty sure this fails. Because it would have said something. Here, but doesn't show. Okay. Okay, let's go back to the node. Let me just make sure I'm doing this right. So if you call this, so if left, we do this, we return, we don't call anything. Here we do call it on self dot left, and yeah. So we do have a left and right. Right? We do have that. Get subtree key count, right? Is that? Yeah. Yeah. Oh, look, we even have heights. Very nice. I don't care. So it equals 1. Yeah, so if you have no children, the value is 1. If you have a left, then we do 1 plus the left. If you have a right, then we do 1. What is this though? We do current count. This is always 1. So I might not need that. Yeah, I don't think we need this. Let's just do that. Let's just do that, just for funsies. See what happens. Okay, well we still get runtime exception. What the heck? What the heck? Alright. Alright, here's what I'm gonna do. I'm gonna put this in a try catch and yep, I'm gonna see what happens. Let's do that. Try accept. Yep. Baddie error. Alright. It's not defined? What do you mean? Oh my god. Can't believe I did that. Alright. Oh, cool. So we did it. We actually did it. Okay. So let's put that back. Let's put that back. Cool. Now we check this. Ooh, we're supposed to do log n. Worst case. Whoa. Oh my god, the worst case. Oh my goodness. Screw this, bro. I don't want to do log n worst case. I want to do linear worst case. Or the node. I don't want to do log nodes, bro. I want to do like the other one. Nth largest key. Gotta be kidding me. You got to be kidding me. Alright, let's figure this out. This can't be too hard, right? Okay, here's my idea. Okay. Here's my idea. After every insert or remove, I'm just gonna call this on the root node, and yeah, I'm just gonna call it on the root node. So they didn't say I could decrease the worst case of the other algorithms. All right, this one is still gonna be log n, but the other ones are gonna devolve into linear time. So there you go. All right. Okay. Wait. Hold up. Nth largest key. What does this have to do with the subtree count? Why'd they make me do the subtree count? I'm confusion. I'm confusion. Alright, whatever. So it says suppose a tree has these keys. This turns 10, this turns 19. Okay. Hell nah, bruh. Hell nah. Hell freaking nah. Alright, let's check this out. So, a naive solution would be... I don't know, actually. What would the naive solution even be? Well, the naive solution... Oh, we would traverse this in order. Right? I hold up my phone. Let me test the chat. That thing's working. Yeah, it's still working. Alright. So we would traverse it in order. And then just yeah. That's it. I mean, isn't that it? Isn't traversing in order log n anyways? So, cause look at this thing, dude. It's right freaking here. And then we do visitor. Oh, we have to make a visitor, which implements that visit. Okay. Okay. You sneaky dog. You sneaky dog. Gotta make a visit thing. This is a little weird, isn't it? Don't I just go in order? And then just stop. Like I maintain a count and then I stop after like a certain amount of visits. I think that's it. I think that's it actually, because yeah. Alright, whatever. Whatever, bro. We're just gonna. Yeah. Look at this. We're gonna make a visit thing, and then it's gonna be like, you know, we got the self, and then that's, yeah, we got node, AVL node. Actually, it's not even an AVL node. It's just a regular flipping node. So yeah. Alright, what are we gonna do? We're gonna do node visited equals this plus 1, and then we're gonna do self dot in. Oh wait, actually, how do we do it? We call it in order with a visitor. Okay, I mean, I think that's it, really. All right, we do in order, like that. Self.root. Is that how that works? You put the node visitor. You don't even. Wait, what? Oh, you don't even have to. Oh, jump scare. Jump scare. Alright, peace out, people.